The last video talked about the Bohr model, kind of what motivated it, and basically what it is. What it didn't do was address just how this got to atomic spectra with any kind of numerical result. So to do that, we're going to talk about atomic spectra kind of specifically. The Bohr model gives these energy levels of orbits that are negative 13.6 eV over n squared. Now, to get there, we need this idea of EV. When we talk about EV, one EV, this is called an electron volt. It's a unit of energy. Energy we have been measuring in joules when we did like macroscopic physics, kind of physics 1 things, and we said 1 joule was 1 kilogram meter squared per second squared, which is fantastic when we are dealing with items that have masses of kilograms or multiple kilograms or even a few hundred grams type of thing. Joules make a whole lot of sense to work with. When we are dealing with atomic spectra, we are dealing with electrons. An electron has a mass, electron mass, of 9.11 times 10 to the minus 31st kilograms. So by the time we get to a joule, we've got a lot of stuff going on. It's nice to be able to do to be able to do energy problems without carrying around all these exponents. So we come up with this unit of the electron volt, and it's just a smaller unit of energy. The electron volt, 1 electron volt is 1.609 times 10 to the minus 19th joules. Later on, when we start doing electrostatics, this number will come up again and again and again, and we'll be able to see where that's coming from. But for right now, we're just going to treat this as an energy conversion. So the energy of any particular level is negative 13.6 eV divided by n squared, for the most part. There are a couple of pieces of this that might be sort of strange. This minus sign, why would there be a negative energy, is the same as we had when we did planetary motion, when we looked at universal gravitation. We said we had a potential energy for gravity that was a negative g m over r way back in physics 1. We get the same thing here. We get our potential energy is negative because these are called bound states. I know we've talked about that before, but a bound state just means this electron is going to be associated with this proton, with this nucleus, as long as our energy is negative, our total energy is negative. If our total energy gets to 0 or positive, then that means that's a free electron. It's no longer associated with the atom. So bound states, same as we did back with planets. We get that this energy drops off with n squared, meaning our n equals 1 level, we get an energy of negative 13.6 eV. Our n equals 2 level, we get an energy of negative 3.4 eV. I'm going to just write out a few of these. So we get some energy levels that look like this. We get a big gap here, right? This is a difference of 10.2 eV. Here we get a smaller gap, and a smaller gap still, and a smaller gap still. So these keep stacking closer and closer and closer together. When we draw these energy levels, we usually draw like an n equals 1 here, n equals 2, 3, 4, 5, to where eventually these are getting really close together. We want to be able to move an electron from one energy level to another, and that's what we do. We say that the energy needed to move from the n equals 1 level to the n equals 2 level is equal to E2 minus E1. So we get E2 minus E1 is 10.2 eV. That's our energy 1 to 2. What that means, if I've got an electron hanging out here in this location, and it absorbs just the right energy photon, then that energy will boost this electron up into the n equals 2 level. We don't have to go from 1 to 2, 2 to 3, 3 to 4. We could go from n equals 1 to, let's say, n equals 4. To do that, we're going to go E4 minus E1. So our energy from 1 to 4 is going to be 12.75 eV. So we can get there pretty quickly. If we absorb a photon with an energy of 12.75 eV, we will jump from the n equals 1 level straight up to the n equals 4 level. If we are hanging out in the n equals 5 level and we want to drop down to the n equals 2 level, then we would say energy 5 to 2, and we're going to again take the difference between those, so we get 2.86 eV. Because we're dropping down, we need to emit this photon. So if we've got this electron that's sitting in an n equals 5 level, and we want it to drop down to n equals 2, then it's going to have to give up a photon. It says, I've got too much energy, I need to get rid of some, so I'm going to emit a photon. Down here where we're climbing, we need to absorb a photon. So now we get to the spectra. When we emit a photon, we might be emitting a photon with a wavelength that gives us red light. The other way we can look at this, so this might correspond to an energy transition of 4 hydrogen. We want to shine full spectrum light on here. So we have this full spectrum light coming in, and it hits our hydrogen. And I'm just going to draw actually this way. It hits our hydrogen, which has an electron sitting in some energy shell. And then we see light on the other side. But what we see is that we are missing this spot. So what has happened, we had our full spectrum light come in, and somehow or other, the electron that was in hydrogen has picked up exactly enough energy to be able to jump from one level to another. And it turns out that this one, if this is my electron, that this is a jump from 2 to 3. Requires a transition of 1.89 eV, which translates to a frequency, or to a wavelength, of 656 nanometers. That is the one that's missing here. So this is for an n equals 2 to 3 transition. Hydrogen has a few of these lines that happen to fall within the visible spectrum. We get this line at 656 nanometers, that's a 3 to 2. We get a line here. So this is the 2 to 3, and that is our 656 nanometers. This one over here is the 2 to 4, and that is 486 nanometers. We get a line over here, and that is our 2 to 5, and that is 434 nanometers, and then we get one more out here, and that one is 2 to 6, and that is 410 nanometers. We do get more lines, of course, like we get one out here that is 2 to 7, and that one's going to be 397 nanometers, but it falls right near the border of UV light, so we may or may not be able to actually see that. What you might notice is that all of these go from the 2 level. Any sort of a transition that goes from 2 to whatever is called a Balmer series line. And for hydrogen specifically, all the lines that are actually visible, that fall into the visible light spectrum, happen to be Balmer lines. That doesn't have to be the case. For a different atom, it might not be. So then we should talk about what it looks like for different atoms. How do we adjust this? Because it can't be the same, right? And it's not. We actually know that the atomic spectra for different elements are different from each other. That's actually how we can identify what's going on. So what happens if we have helium? How is that different? Well, helium, instead of having a single proton, has 2 protons and 2 neutrons. So helium, where hydrogen had just the 1 proton, hydrogen has an atomic number of 1, or a nuclear charge of 1. Helium has 2 protons, it has a nuclear charge of 2. So our Bohr model, our energy levels are actually going to be negative 13.6 eV multiplied by z squared over n squared. And now we have adjusted this to account for different nuclear charges. There is still a problem, because this is assuming that we have 1 electron. Helium has 2 electrons, so the Bohr model works particularly well for what we call hydrogenic atoms. And hydrogenic atoms are those with one single electron. So we've stripped away, right, if we've got carbon, carbon has a Z of 6. So if we wanted to look at carbon, we would want carbon 5+, meaning we have removed 5 of the electrons. Then this will behave reasonably well. Now we can relate these energies to a different thing. We can talk about the energy of a photon. Remember, a photon is just a particle of light, for however strange that might sound. The energy of our photon is equal to h times the frequency, and h is something called Planck's constant. Which has a value of 6.626 times 10 to the negative 34 joule seconds, or 4.136 times 10 to the minus 15th electron volt seconds, whichever way you want to look at that. We have this, we know that F times wavelength equals c, so F is equal to c over lambda, so we can also say this is hc over lambda. This is particularly convenient because h times c, this is just a constant, it's not changing at all, and we can make this shortcut. H times c in the right units is equal to 1240 electron volt nanometers. So then if we've got the energy of a photon in electron volts, we can find our wavelength in nanometers quickly and back and forth. Either way, this is the energy of the photon. The next video will be working through some examples.